Hey, how are
Hi.
you?
Let me turn on the volume.
Mhm. How are you?
Good. I'm good.
Cool. Yeah, it seems like you're back home.
Yep. Just arrived.
Yep. No more biking.
Yeah, I biked.
Okay, got it.
Yeah.
All right, yeah. What would you like to go over?
Um, since we did biochem yesterday, I guess we could do the other campus passage.
Mhm.
I think I sent you two on Monday.
Yeah, let me see. Okay. Passage 7.
Yes.
Is that the one? Okay. Yeah, could you open that up so we can take a look at it?
Yeah.
Mhm.
I have both of them open. Let me know which one you prefer. Like I have this one and this one, like answer and without. Yeah.
Um,
I mean, this is cleaner. That's why I like reading this more.
yeah, the other one you can even just like hit the hide explanation. Yeah. Well, I guess it still kind of shows you what the answer would be, but yeah, whichever one you'd like to use. Um, but yeah, let's have you start reading
Yeah, this one's less thing.
passage. So remember, um, so let's have you practice identifying buzzwords. So and do you remember what those were? Like
Yeah, like
meaning? Mm-hmm,
usually they'll ask questions about like content.
mm-hmm, mm-hmm. Yeah, good. Okay, yeah, why don't you start it off?
Okay. The central nervous system stimulant caffeine can be extracted from commercial no-dose tablets. Pure caffeine has a melting point of 235 and a density of 1.23. The solubility of caffeine at standard temperature is 0.14 in dichloromethane and zero point zero 0.02 in water. Okay.
All right, and so Um, okay, so I guess they're just giving us, some of these physical properties of caffeine that, we might have to do some math about. Um, but yeah, you can continue. So tell me about, yeah, continue.
To extract caffeine,
Oh,
a
when you continue, like, you know, the next thing would be the figure one.
um, so this is the structure of caffeine,
Yeah. So whenever they give you a structure or structures, what do you want to look for?
the functional groups,
Correct. What functional groups do you see here?
and amide,
Show me where.
uh, here,
Uh-huh. Can you show me this specific amide bond?
here,
Uh-huh. Do you have any others?
um, here,
Yeah,
and
keep going.
here.
Good. So we have, yeah, three amides. All right, what else do we have?
Um, I guess we have, I don't know what it's called, but it's like uh, a ring with nitrogen.
Well, yeah, heterocyclic ring, five-membered heterocyclic ring with two nitrogens. Um, is that does that look somewhat familiar? Like,
Familiar in what sense? Sorry.
uh,
Like this reminds me of like pyrimidine, sorry, like purines, like nucleotides,
what
just because of the like two rings. Sorry.
about just this one that I circled?
It looks familiar, but I guess I don't know what I should be comparing it to or what I should be thinking about.
Got it. Yeah, um so yeah, this is a typical type of um heterocyclic ring called an imidazole.
Mm.
And you would see it. I mean, what I circled, not necessarily the methyl here, but and you see this in something like histidine, right?
Yeah.
Because that has an imidazole ring in its side chain, right? So yeah, so you want to look at this and you want to recognize functional groups to the best of your ability. All right, cool. And yeah, I guess we can continue.
To extract caffeine, a no-dose tablet, 10 grams each, was crushed and added to 100 milliliters of distilled water and boiled for 10 minutes.
Okay.
Suspended solids were removed, and the supernatant was transferred to a separatory funnel.
Okay.
Okay, they're extracting it. Next, 100 milliliters of dichloromethane, DCM, was added to the separatory funnel, and the mixture was shaken, which resulted in the formation of two layers. Each layer was separately collected, and the aqueous layer was poured back into the separatory funnel for the extraction to be repeated.
Okay, let me ask you this. What is a separatory funnel?
It's sort of it's like a device that you use in a lab to like separate things to
What would it look like?
um like uh like this. I don't know.
See if you
Like
could,
narrower in the bottom, wider at top.
huh? So would it just be like a regular funnel like that?
Um
Because this is like a regular funnel, right?
yeah.
Um, is that what it would look like?
You have like a stop thingy on the side that allows you to control uh but
Or would it look something like this?
I feel like there could be both, right? I don't know. I feel like I've seen both.
Uh-huh. Yeah. So yeah, I just wanted to okay, what else can you tell me about separatory funnel? Like when is something like that used?
When you want to like increase the purity of something, like you want to have a specific like if you have an impure substance and you want to purify it or you want to increase your something, like you want to separate something
Okay,
from.
good. So um so this would be a separation, right? Technique.
Yeah,
Um Now what types of extraction exist?
like methods.
Just types. Well, I guess methods, but well, actually more so just like a broader category of types. Um, so I get essentially what I'm trying to say is that, if you wanted to separate solids from liquids, you would just need like a filter, right? Kind of like a coffee filter. Coffee filter will have like the solid coffee grounds in it, but the water can pass through the filter. So if you want to separate solids from liquids, you could just use a filter. And so that would just be filtration. Right? And if you wanted to separate liquids from other liquids, you can't use like a filter, right? Unless it's some type of filter that can separate something from a fluid or liquid from something else. But typically speaking, you can't really just use a mechanical filter like that. So this would be, so like, yeah, this is filtration. This is extraction. So when it comes to like separation techniques, I want you to consider like what phases we're trying to separate. And from there, you can think of what property can I exploit, or what property can I take advantage of to be able to separate these things, right? So, I mean, one type would be like, condensation, right? Where you can have two liquids in some type of whatever flask system that you heat to cause something to evaporate, and then you like condense it back down into liquid and you can collect it. So that type of thing takes advantage of the fact that the two liquids that you're trying to separate here have different boiling points.
Is this distillation?
Yes. So, so yeah, but it's under the broad topic of separation techniques. And when it comes to that, you just want to think about what is different between the things that we're trying to separate, and you want to take advantage of that difference. So if two liquids have different boiling points, you can use distillation to have the one with the lowest boiling point evaporate first, and then it can get condensed into this other container here, and then whatever's left here will be that other liquid. And that's just taking advantage of the difference in boiling points. But let's say that there isn't much of a difference in boiling points. Or let's say that the difference in boiling point could be there, but we can have another property that we can take advantage of. Like if we created, if one of the liquids is like hydrophobic and the other liquid is hydrophilic, you can put it all in that separatory funnel and, shake it or whatever, and you'll have the hydrophobic. So like inside you'll put in, the solvents like water for the hydrophilic layer, and some organic, non-polar thing for the organic layer. And whichever liquid is more hydrophilic than it is hydrophobic will end up in the aqueous layer, and whichever liquid is more hydrophobic and like lipophilic will be in the organic layer.
Yep.
So yeah. So basically the buzzword here is separatory funnel and extraction. Okay, so we see that separatory funnel here, extraction here, right? And it can also help to like, so when you read like this stuff, do you like imagine, like, do you like visualize someone doing like the experiment or or anything?
If it's easy to follow, yes, like this.
If it's what?
If it's like, if I can follow it, yeah.
Uh-huh. Yeah. So like for instance, when you were reading this, this is how I processed it. Like I was thinking, all right, someone's taking one no-dose tablet, crushing it, taking 100 milliliters of distilled water threw the crushed no-dose tablet into that, boiled it for 10 minutes, and it seems like some solids formed, but they removed it. We don't care how. But the supernatant, uh, which is not that solid stuff, is what we're left with. And we put it in a separatory funnel, and then you take dichloromethane and you take 100 milliliters of dichloromethane, and you add it to the separatory funnel, and you shake the mixture, and that should cause two layers to form. And one of the layers should be an aqueous layer, and the other layer would be the layer that has the organic layer. So that would be the layer that has the dichloromethane, I think, right? So like that's what I mean about like visualizing. Like, do you visualize it that way?
Yeah.
Okay. So okay. Now okay, so dichloromethane was added to the separatory funnel, then they're in two separate layers. Um
No.
do you think
Mhm.
so if I drew this over here, like with this layer over here and this layer down here, which one do you think will be the aqueous? Which one do you think will be the organic?
I knew you were gonna ask this. Um, I'm going to say I think the aqueous will be on the bottom.
Tell me why.
It's just how I envision the interaction of oil and water.
Yeah. Now, I thought you were going to say that because a lot of times people say that, right? Um, using that example that you mentioned of oil and water. But what ultimately decides what's on the bottom and what's on the top?
Density.
All right. And what's the density of water?
Is it like one?
Uh,
Maybe it's one, right? Yeah.
1 gram per milliliter, right?
Yes.
So, and what's the density of the dichloromethane here?
1.33. Okay. Yeah.
So we're used to seeing the extraction thing drawn with the organic layer on top, and we're used to in real life thinking about oil floating, on top of the water. Um, but it doesn't doesn't mean that it will like there's nothing about it that would make it so that it's always going to be on top. The density is what will tell you what will be on the top, what will be on the bottom.
Okay.
So, okay, now let's see. So we have the two layers, and each layer was separately collected. So I guess they like took the organic layer and they put it into like one flask, the aqueous layer in another flask, and then they put the aqueous layer back into the separatory funnel to repeat the extraction. Okay, so this is like a fractional type of thing. Um, so yeah, when they did it again, they used 100 ml of DCM again, and then they did the extraction again. And then after that extraction was done, the layers containing caffeine from both extractions were mixed together. Okay. And the resulting solution was boiled gently until a white solid formed. Okay. To determine how much caffeine was expected to dissolve in each layer and how much caffeine was extracted in total, following formula were used to determine the partition coefficient of caffeine. So I'm imagining them doing this extraction, and they collected in one beaker the organic layer and another beaker the aqueous layer, and then they put it back into the separatory funnel, and they did it again. And then they boiled it, and some type of white solid formed. And then they're giving us these equations. So equation 1 seems to be like the solute concentration in the organic layer over the solute concentration in the aqueous layer, right? So what would the organic layer be made of?
The DCM.
And what's the solute?
Caffeine.
Good. So, okay, so this partition coefficient calculation, I guess, is equal to the concentration of the solute in the organic layer over concentration of solute in the aqueous layer. Actually, I want to, if we go back up to figure 1, what do you think what layer do you think this would be in?
The DCM.
Yep. Why?
Well, the structure, but also it's telling me the solubility of caffeine in both.
Oh, yeah. So you see that there's more of a solubility in dichloromethane. All right, yeah. Good. Yeah. So I think most of the time they may not give you that, but you did a good job in both being able to determine that from the figure, and noticing that. So good job there. So okay, let's go back down. So yeah, solute in organic layer over solute in aqueous layer. Okay, and then the next equation is the approximation for an extraction. So what is this I thing? Oh, solubility of a solute in a given solvent.
Where are you reading this?
Oh, all
I
down here.
Oh,
Yeah. So solubility of solute in the organic layer over solubility of solute in the aqueous layer.
I
Uh,
see.
yeah. Okay. So, all right, we
This
have that.
is
Yep.
reminding me sort of like actual year yield versus like expected yield versus actual yield, kind of. It's an approximation.
Uh-huh. I think the actual and theoretical is like what you should theoretically is what you should be getting, and then actual is what you get when you do the experiment.
Yeah.
But I think this is just like giving us equation 1 to get a precise value for the partition coefficient. And equation 2 is just a way to approximate that partition coefficient. So okay, so we see that. Let's see. After completing the extraction, recrystallization was performed. Okay, what is that?
You're forming back the crystal, so like you're going back to solid is what I'm thinking.
Tell me a little bit more.
Um, it's also used for like a purity thing, I feel. Like when you're um trying to do extraction. I feel like it's also like a separation
Yep.
technique, recrystallization.
Yeah. So what it essentially can let you do is separate like solids, essentially. Um, for the recrystallization. So okay, so after the extraction, they did recrystallization, and then Oh, so yeah, I'll write that. So like separating solids from solids could be uh recrystallization. Um, and what that typically means is that they're going to take the solid, they're going to dissolve it in something, so it's no longer like a solid, it's kind of like aqueous or whatever. And then they're going to slowly like cool it again and let the liquid leave to reform that solid, but it's going to be a more pure uh, sample of that solid.
I
Um,
see.
yeah. So they're talking about recrystallization. So you want to be thinking of like now solids, and then they're saying ethanol was added to the white solid. That's exactly what we're expecting, that we're dealing with solids here. And the solution was gently warmed and allowed to cool down to 25°C room temperature. So, and that's exactly what happens with recrystallization. Um, the solution was then placed on ice until crystals formed. Um, the crystals were vacuum filtered and tested for purity via melting point determination, IR spectroscopy, and TLC plating. Um, so, so why is a melting point a good way to determine purity?
Because each compound has a unique melting point.
Uh-huh. Um, think about though, because that's true, but think about like why, because like they don't have to give you like the melting point information, but think about an impure thing, its melting point compared to a pure thing.
I'm thinking, and I may be wrong, but I'm thinking that the melting point will be higher just because it has more solutes, like it has more things in it.
Yep. So this is under the category of colligative properties, right? Colligative properties, you know what I mean by that? Like they're based on the amount of like solute that you have. Um, and so things that you might experience for that would be like boiling point elevation, uh, freezing point depression, um, osmotic pressure, and vapor pressure depression. Um, so yeah, it makes sense that they would use the melting point to determine the purity, because the more pure it becomes, the melting point should go up, right? The melting point is also the same point as the freezing point. So if solutes cause the freezing point to go down, it means that it causes the melting point to go down. So the more pure it gets, the higher the melting point will be.
The more pure, the higher the melting point,
Mhm.
not the lower.
No, because the colligative properties, right? They're all about solutes.
I guess let me, because I think I'm thinking of boiling point.
Mhm.
Uh, because boiling point should be lower, right? If it's more pure. Or am I getting this wrong?
Yeah, so yeah. Mhm.
So for melting point, um, you said melting point should be higher for pure.
Uh-huh. Yeah, so I drew this like kind of heating curve here. So with, let's say this is like temperature, as we add temperature to a solid, right? It's gonna solid temperature will rise until it reaches this point, after which its temperature will plateau because the energy that you're adding in the form of heat is going to be contributing to breaking the intermolecular bonds between the solid, turning it into a liquid. So we can think of this as the melting point here, right? But if we're going in the opposite direction, let's say like this, right? Where it's like gas to liquid, and then liquid here, and then liquid to solid, and then solid here. Liquid to solid is freezing, right?
Mhm.
So this temperature here is both the freezing point and the melting point. Like whatever temperature that is.
I see. I see.
And so we know from colligative properties that the more solutes there are, aka the more impure something is, right? It will cause one of the things it'll cause is freezing point depression. And freezing point is the same point as the melting point. So if it was impure, the melting point should go down. But if it's pure, or the closer we get to it becoming pure, the higher that melting point should be.
I see.
It's like
Yes.
when, yeah, it's like when the reason that when people anticipate snow, they put salt out in the roads and stuff. Why do you think they do that?
Um, I don't know. I mean, I guess I'm imagining it like melts the snow.
So let's think about,
Solute. It's a particle.
uh-huh,
You're like pollute, like making it more impure.
yep. And if you do that, yeah, continue.
Um, if you do that, you have the freezing point depression. So like at a lower temperature, you're going to be able to melt it as well. I see.
At a lower temperature, you mean you'll be able,
Sorry, I guess I get confused when I talk about temperature, but
yeah.
like instead of it being like it needs to be I don't know, like zero, I don't know, 0 degrees to melt, like maybe it'll melt at 4. So it's increasing the temperature. I guess I get confused when I think of temperature.
Okay,
Yeah.
okay. So what you said about melting point, remember that melting point is the same point as the freezing point. So let's say that we did not put salt out. Then we just have pure water essentially, right?
Mhm.
And at 0 degrees Celsius, right? This is going to freeze, right? So how can we stop this from happening? Well, we can add salt, which will dissociate and create impurities due to the solute, which would lead to the colligative properties, one of them being freezing point depression. So now the freezing point will go down. Let's say it goes down to negative 15 degrees Celsius. That means that if it's 0 degrees outside, without the salt, you'll have ice and you can slip and fall and stuff. But if you add the salt, the freezing point goes down. So it has to be so at 0 degrees Celsius, it's not going to cause ice to form. Um, it would require a lower temperature for the ice to form,
I see.
right? There's
I see
also
that
Mhm.
freezing point depression. Okay.
Yeah, yeah. Because like what you were saying, like you were on the right track, thinking like it will cause it to melt, but it's if it causes it to melt, it would let it get frozen in the first place, right? But the good thing about being able to use salt like this is that instead of having it freeze and then melting it, you are preventing it from freezing in the first place.
I see.
So another thing could be like, when people add like when people like boil water for food or whatever, they add salt. So what do you think that could be related to?
Um, they're trying to boil water and they add salt to the water. You're adding an impurity.
Huh?
Um, but that would raise the boiling point.
Yep.
So, like, you need to increase the heat for it to boil over, I guess.
Uh-huh.
So it won't boil over, maybe. I don't know.
Yeah,
Yeah.
yeah. So it would cause boiling. So anytime you're dealing with solutes in a solvent, um, and I guess when I say solute, I mean like solid solute, right? Um, well, solid, yeah, but I mean it can of course dissociate like salts do. Uh, but I guess technically it'll still be solid even though it doesn't look like it. But yeah, if you did that, then so let's say that, you're cooking something at 100 degrees Celsius and whatever, it takes you like 15 minutes or something. Um, if you add like some salt and stuff, let's say it causes boiling point elevation. Let's say the boiling point is now 115 degrees Celsius. That'll take you less than the 15 minutes.
I
Uh,
see.
that way you're able to cook something at a higher temperature without the water like, boiling away.
I see.
Yep. Um, it's also why you could put like alcohol in like the freezer.
Uh, yeah, because
Because if
it
it was just water, if you put it in the freezer, it would freeze. But alcohol, which is like water mixed with like ethanol, will have those. I mean, I guess technically, like we can call them impurities. But that would raise the, or sorry, that would lower the freezing point. So, so in a freezer, which would normally freeze water, uh, alcohol with its lower freezing point, won't be frozen. It'll have to be colder.
Yep. Unless
So yeah. What's up?
unless you add in water to it, I guess.
Uh-huh. But it's already like, if it's like a 40 proof thing or whatever, I forgot how it went. If it's 40 proof, I think it's eight. Is that 80% alcohol? Or do I divide it by two to get 20%? I forget. I divide it by two. So if it's 40 proof, that's 20% alcohol. So we can essentially just say that it's 80% water. Uh you could probably even do like an experiment with taking like a beer that has a low alcohol content and then something with a higher alcohol content. And I bet if you did like an experiment where you tested the freezing points for each, you'll see as the percent of alcohol increases, the percent of water decreases, and the freezing point should decrease as you move forward.
I
Um,
see.
but okay, good, good, good. So that's the stuff about yeah, melting point. So think about those colligative properties. Um, all right, and I respect and all that stuff, and then TLC, DCM was used as the solvent system. Um, and 3 spots were placed on the TLC plate. So one for the crude extract, one for the recrystallized caffeine, and then there's a pure caffeine sample. So, okay, so it seems like the crude extract, what do you think that would be here?
Um, yeah, well, the way I'm thinking of it is just like I'm thinking of like negative control, positive control, and like your sample of the crystallized caffeine. Yeah, I don't know. For
Well,
crude
let's think about what that crude extract is, though, right? Because if we don't know what it is, we can't tell if it's any type of control, right? So
right?
use the passage information. Or what can you can also do is look for the other stuff that they mentioned.
Um, like for these others.
Yep. So like for instance, recrystallization, right? Or recrystallized caffeine. It's
Yeah.
what's happening here, right?
Yeah.
With, them adding uh the ethanol and that stuff. So that's the recrystallized caffeine. The crude extract, right? That would be the stuff before the recrystallization, right? Like, yeah, here, essentially.
I see. Oh, I see.
Mhm. Yeah, I don't know yet if it's just that first extraction or if it's the two extractions, but I at least know that's where, that will be mentioned. So we have all of that. And then we have our,
We have like 3 levels of like purity.
uh-huh,
Yeah.
yeah. So, yeah, so the crude extract should be the least pure. The recrystallized caffeine should be more pure. And I think the pure caffeine sample is just that could probably be the positive control. Well, I guess depending on what you're looking at, it could be positive or negative, but the pure caffeine sample, I think they didn't mention that being an experimental thing. So I think that that's just the theoretical kind of thing for pure caffeine. So, all right, so we have this information down. So the buzzwords here were extraction, separatory funnel. I mean, you know, separatory funnel, when you see that, you should be thinking extraction. And when you see extraction, you should be thinking separatory funnel. So they should be connected as well. Um, but uh, but yeah, and then yeah, just visualize the steps and that kind of thing. So um yeah, and I think we're good. Like this thing over here, like I don't know what we're gonna do with this. It's not something that I understand right away from looking at it. Like solubility, like we're not even really given solubility values and stuff. So, but we don't have to really worry about all that stuff when we were reading it for the first time because we just need to answer the questions. So, all right. So, yeah. Uh, any questions on this?
Nope, but we do have the solubility.
Oh, good job noticing that. Yeah. Okay, okay, okay. That's good. That's good. That's good. So we can make a pretty easy approximation then, right? Of the whatever thing. So it's like 0.07, I think, or 7 or something. 0.02 goes into 0.147 times, right?
Yeah.
So, and that's what that approximation thing was saying, right?
Yeah.
All right, cool. So we can, yeah, so we already know yeah, what to look for in that regard. So yeah, good job. Good job at noticing that. Um, okay. They'll probably also ask you stuff because they're saying pure caffeine has a melting point of this. So I suspect that they'll ask us something about like what's the melting point of the crude extract or what's the melting point of the recrystallization. And they should all have uh like okay, so like the crude extraction, the recrystallization, the pure sample. Now, melting point again is the same thing as freezing point. Um, what do you think the melting points would be for these, I guess? So like pure, we know it's 235.
it should be lower
Mhm.
for the other two.
Yep. Oops. Good, good, good. Okay, awesome. All right. So here we go. Question 36, exactly what you would expect because they love asking questions about what functional groups do you see. So, uh, so yeah, how do you do this?
So the way I did it was like I identified the amide um and the types of amines that we have. So like how many groups are bound or like carbons are to the nitrogen. And we don't have a primary amine, so we don't have like an NH2 group, NH2 or NH3 group. So I feel like that is not the one that's not there.
Okay.
Is it
The
NH3, right? We don't have an NH3.
what was that at the end?
Um, it would be we don't have like an NH3 group.
Uh-huh. So you're able to know what an imide was?
Um, so when I went over this, I knew what an amide is, like B. Um, and so like I think I went through like process of elimination for C and D. That's how I arrived at C. Um, and then if I remember correctly, the imide is like sort of like the carbonyl, but like with the nitrogen is what I'm thinking. Or am I wrong? Sorry?
Oh yeah, yeah, yeah. Yeah, it's basically like a nitrogen that's flanked on both sides by carbonyls.
Let me look it up to make sure. I see. Yeah. Okay. Yep.
Um, so so okay. Yeah, so I think like imide is not really very well known. Did you know what it was when you answered this question?
I think I've seen amides before, so I knew it was like a carbonyl and a nitrogen.
Oh, wait,
Uh,
I mean imide, this one?
yes,
That's right. Okay.
yes. And so I wasn't completely sure, and I see similar things in the structure. Like I remembered like carbonyls and nitrogens, that part. And so I just went towards the other options because they were more obvious. Um,
Okay. So so yeah, because this could be a good example of like what to do when you don't know. Because I mean that's also like most, like what it, it's gonna be the reality of the MCAT. Like you're not gonna know everything, but you want to be able to still make the best decision you can make. And that comes with like doing kind of like an appraisal of how confident you are in the choices. So for instance, we know amides are here. We know tertiary amines are here, right? And let's say we don't know what this imide is, but we do know what a primary amine is, right? And we know if we know what a primary amine is, we can determine if figure one contains any primary amines. Does it? No, right? So this, whatever it is, right, it must be present there because we know that a primary amine is not present. So a lot of times, you're going to go with like probability. And when it comes to probability, you want to start off with things that you know for certain. and go, yeah, and essentially just go in that direction. So, yep, good job. All right, so some math, which I guess we were going to be expecting.
Yeah, I don't think I even attempted this question.
Yeah.
Yeah. Um, how much total caffeine could you expect to extract at the end? Um, I guess when I saw this, I was thinking like, did they mention like what is it, like a yield in each step? Or but they didn't. Um um,
Mm-hmm.
oh, okay, I see. Expected to extract. So I guess these formulas.
Yep.
Um yeah.
So,
It's like, because this is expected to dissolve.
uh-huh.
Uh okay, how much caffeine is extracted in total?
Mhm.
I see. Yeah. So we kind of went with 7 earlier from this calculation, but it's per milliliter. Are we giving the amount of milliliters? And I guess we just have to multiply it by that, is my thinking. Um, we start out with 10 grams, added to 100 milliliters of distilled water. Is it this that they're referring to? I don't think so.
So, um, so okay, what they did was they so the solubility um of caffeine in the organic layer compared to that in the aqueous layer um would give us, that partition coefficient, and then we would just multiply that by um the volume of like the milliliters, right?
Yeah, I understood that. I guess I just get confused on what volume we should multiply it by.
Mm-hmm.
Uh,
Uh-huh.
I'm thinking. I guess it's just in the amount of like solvent probably.
So we see that. So if we look at, oh wait,
Or-
yeah, the here. So what we're doing is that we are using 100 mLs of water and 100 ml of DCM, right?
Yes.
And I mean, they do another extraction, but that second extraction, it's still using 100 ml of each, right? So go with that. Go with the 100 ml value.
Okay.
Um, and let's go from there.
Did we do this right? Was it really 7 or was it, let me see.
Mm-hmm.
Yeah, it's 7.
So that 7, by the way, doesn't have a unit, right? Because the units cancel.
Yeah.
So, but what it means is that in DCM, right, that the constant, so like if you go back down to the two equations, these could be equated to one another. So we got for this 7, right? And we can equate it to this. So this is solute or caffeine concentration in organic layer over caffeine concentration in aqueous layer, right? That's equal to 7. So, well, now we have concentration values. Concentration values are like, moles per liter, right? So to kind of like get the liters out, right? We would have to multiply it by some value for liters, right? Which could be multiplying it by like, if it's 100 mLs, you can use that. So, yeah. So let's try it like that, right? So like the 7 here essentially means if I rearrange it, it would be 7 times the concentration of caffeine in the aqueous layer is equal to the concentration of caffeine in the organic layer. So caffeine is 7 times more soluble in the uh, organic layer than it is in the aqueous layer, right?
Yeah.
So uh, so now we just have to solve for the amount of caffeine that you would get. So we can just kind of like multiply these sides by the 100 mLs, right?
No, I mean, I guess what I understand why you're equating it.
Uh-huh.
Um, and we have 100 mLs, right? But we don't have any like mole value, do we? We don't have any we don't know how much caffeine, right?
Um, yeah, so what we can do, right, is we can use the like, okay, let's see. So a no-dose tablet is 10 grams. They didn't mention anything about like what percent of that 10 grams is caffeine, right?
No.
So we can start off by saying, oh, okay. So yeah, let's start off with then 10 grams of caffeine, right? And
Okay.
then if we, so yeah, 10 grams of caffeine, we can say, um, and then for, um, for the, let's see, see, 7. Okay, let me try. I'm gonna try this fresh. So we can have this it being equal to, yeah, because I realize this may not. All right, let me just see. So I'm just gonna do it. So this over that. Um, That's the thing that will give me the seven. And okay, so let's see. So I think we can eliminate two choices, even without doing the math that I just did. If you consider how much we start off with.
With 10 grams?
Uh-huh.
Yeah, that's true. You won't have more than C and you won't have this for sure.
Good. Yeah. So always do stuff like that to make it. So yeah, now it'll so now I guess yeah, would it be 6.5 or 9.84, right?
Oh, I see. I think I get it now. It's, I guess if I think of it as percentages, it makes more sense. Like if it's, is it sort of like the 7 grams that we get of 10 grams is like 70%? Um, so like if we start out with 10 grams, then you would expect something around that 70%. Maybe.
Tell me what you said about the 70%,
Yeah.
the
So
percent.
this partition coefficient, it's sort of giving us an indication of like if we started out with 10 grams of caffeine and we expect to extract around 7, that's around a 70%. I'm thinking in terms of efficiency, like 70% of extraction. And if we start out with 10 grams, then I'm thinking we should expect something around 7, just in terms of like the approximation,
Mhm.
maybe.
Yeah, so okay, so we have our partition coefficient of 7, which means that caffeine is 7 times, more likely to be in the organic layer than in the, water layer. And then for the extraction, you start off with 10 grams. And I guess we have two extractions in a row. So the first extraction, you would use the partition coefficient to figure out how much caffeine will actually go into that DCM, um, the DCM solvent, right? So, um, so that would be the so okay, most of it. So I guess what you're saying with the percentages, we start with 10 grams, and in the first extraction, let's say this is aqueous, this is organic. Um, like 7 times as much of it would be 7 times as much of what it is in the aqueous layer would be what it is in the organic layer. So yeah, I would say maybe we can say then that, like maybe 7 grams here, 3 grams here. Um, but then you do it again.
Another option. Yeah.
Yeah, you can do it again. Um, so yeah, I think that will lead you to get um so you would get something close to this 7 here. Um, and then for the second extraction, you're gonna, separate that out. So you're gonna get some value that's like, let's say, like 5. Oh, and 2 here. So it's gonna be like if we have start off with 10, right? 5 is in the middle, right? Whoops. 6.5 is here. 9.84 is here. So if it's going to be more so in the aqueous layer, it'll be closer to the 6.5 than it is to the 9.84. So I think what you want to think about it as is, I think the partition coefficient would be the easiest way to think about this because it just shows you that you're going to have a lot more of it, 7 times as much of it, in the organic layer. So since they're using that organic layer twice to do the extraction, to get how much caffeine was extracted in total, then you would get something that can't be greater than 10, but it will be closer to 10 than it would to like the 5 or something smaller because of that partition coefficient.
I see.
Yeah. I wouldn't worry too much. I wouldn't worry too much about the specifics of the math. I would just think about it can't, so like get rid of C and D, and then from there, we are being told that with the partition coefficient, we're being told that 7 times more caffeine will be in that organic layer than in the aqueous layer. And when you're extracting it, you're taking advantage of the fact that it's going to be mostly in that organic layer. So we're going to see something that will be the amount of caffeine that we would expect to extract will be almost like all close to how
Just
close to
10.
like
Yeah. And
yeah.
I guess procedure of the experiment, perhaps you're also including like recrystallization.
Oh no,
No?
because they're just saying extract, and recrystallization is after you complete the extraction.
Okay.
So, so yeah, the procedure is this stuff.
Okay. So it would be 9.84.
Yeah, I would say so. Just because, like, of this partition coefficient being 7, that makes it so if you did the experiment with, let's say, organic layer, aqueous layer, and let's say X is the number of grams of caffeine, right? Um, in aqueous, in the organic, it would be 7 times X. So you just have significantly more of it in that organic layer compared to the aqueous layer, which makes it so that you can separate these well. Like put the water stuff here, put the organic layer here. Like let's compare it to like if this partition coefficient was 2, right? You're gonna have just like twice as much in the organic layer compared to the aqueous layer. And you're going to be losing a lot of that caffeine because it's the solubility difference isn't that great. But the greater the solubility difference, because extraction is all about taking advantage of the difference in solubilities. So you want that solubility difference to be as large as possible. And so, yeah, something like 7 is pretty large. I mean, like, we don't really have a good baseline to compare it to, but I would say that, you know, let's say equal solubility in both water and in the organic layer, you're not gonna, if that was the case, you'd probably get 5 grams.
Yeah, I think I got it too.
Yeah.
All right.
Mhm,
So let's try the other one.
mhm. I knew they're gonna ask this. So,
I don't know why that's selected from before. I'm not selecting it. It's just I'm trying to get rid of that. I don't know how. Yeah, okay. In one trial of this experiment, significant impurities were detected in the extracted caffeine. Based on the results of the experiment, which of the following would be the expected melting point range for this extracted sample? Um, so we know that it has impurities and melting point follows the same trend as freezing point. And I think we wrote this down earlier.
Yeah.
But so we should expect it to have be lower than 235. So I'm gonna go, wait. So not C is my guess right now. And they're all lower, 235. But I guess the range may be important. Um,
So you eliminated C, right?
yes.
So what else? And you eliminated it because?
So pure caffeine has a melting point of 235,
Uh-huh.
and this one has impurities.
Yep.
So I expect it to be lower
Uh-huh.
than 235.
So if you got rid of C, what else could you then get rid? Yeah. You get rid of B. Good. Um, now what?
The range.
Okay.
I feel like I don't know. I feel like my range may be higher if it's more impure. That's my guess.
So
But yeah,
um
like long, like wider. Yeah, I don't know.
yeah. So okay. So um okay, yeah. Let's think about, I guess, well, um trying to think, okay, so this is the one with impurities. So like if it was a pure substance, the range will be very tight compared to if it's not a pure substance, right?
Yeah.
So I think it would be A. Can you check?
Yeah, yeah, it's okay.
Yeah, because a pure substance should have a sharp range for its melting point and boiling point and stuff, right? But if it's impure, that's where you'll have it lower, but it'll be a broader range because of all those impurities.
Yeah.
So yeah.
Yeah.
So but for this, we use, the same type of tactic. Pure would be the highest, right? Melting point is the same as freezing point. Colligative properties mean impurities, aka solutes, lower the freezing point, aka lower the melting point. So if the pure melting point is 235, impure must be less than 235. B and C are out. And then it's a matter of it's 50-50, so already that's good. But yeah, then it's a matter of, is it going to be that sharp range of D or the broad range of A? And I guess just add to like your knowledge, just that because usually this doesn't come up as colligative properties, but it should be added to that. That in addition to the freezing point depression and all that stuff, you will have a broader range for whatever that freezing point, melting point, boiling point would be.
Yep, that makes sense. Last one. Which of the following statements correctly describes the methods used in the experiment? 1, the retention factor in a TLC procedure depends on the solvent system, temperature, and the adsorbent.
Yeah.
2, a polar compound will exhibit a smaller retention factor.
Oh, I was gonna ask, what do you think of that Roman numeral 1?
So my only thoughts here, like I agree with almost everything, except I'm not sure about temperature. Like if the temperature will influence the like TLC plate. Um, yeah.
Tell me a little bit about the TLC like process or procedure.
So I'm imagining like a thin piece of paper or something. And adding we have like you add dots like at the beginning of like where your samples are as and your solvent front is going to travel upwards and like it's usually the stationary is polar and your unless I'm wrong and your solvent is non-polar and so your like mobile phase is non-polar so you calculate this retention factor which would indicate like how far up to closer to the solvent front your samples traveled um and usually this is less than 1 because if it's more than 1 you can't really calculate it because it's like past the
Okay.
yeah.
So for Roman numeral 1, you agree with solvent system, you agree with absorbent,
Okay.
unsure of temperature. So let's leave it like that for now. I'll show you like what we can do. So now tell me about Roman numeral 2.
A polar compound will exhibit a smaller retention factor on a normal phase TLC plate than a less polar compound. Um, I think it's true.
Tell me why.
I think it's correct.
Yeah, tell me why.
Sorry?
Oh yeah, tell me why.
Because the stationary face of the TLC plate or most of these procedures is polar. Um, and so because it's polar, it's going to attach stronger to like the plate and less to like the mobile solvent front. And so it's going to travel less up, like less farther up.
All right. Roman numeral 3.
Anhydrous methanol has greater eluting strength than pentane when used as solvents in a TLC procedure. So one of them is capable of hydrogen bonding. That's what I'm thinking. Like methanol is an alcohol. The other is non-polar.
So kind of like two things there. So like, pentane is non-polar. The anhydrous methanol would be polar then, right?
Yeah.
All right. Um, try to. I think you can uh kind of like answer it from there.
Mm, like the question itself or just point number 3?
Just 3.
Just 3. Um, um, eluting
Maybe
strength.
eluting strength is kind of confusing.
Yeah.
Yeah. All right. Yeah, that's kind of a weird word to use here because when we think of when I usually think of eluting, I think of something coming out. But for chromatography, the eluting strength will mean essentially like how far it goes, I would say. Like it can like eluting strength would in for chromatography would be like how far something can uh travel up like the plate.
I see. I
So,
guess my question here is like when they say eluting strength, are they referring to like the mobile phase, like the eluent, like the solvent? Is that what they're referring to?
uh, so yeah, uh, because that will help it move up the plate more. So, okay, let me show you something that we can do with Roman numerals. So let's start with what you're completely certain of, which is Roman numeral 2. All right, greater than sign. And then we have Roman numeral 1, which you're certain of the solvent system part and the adsorbent part. You're unsure of the temperature part. So let's say for Roman numeral 1, you're 2/3 like sure, you're 67% sure. Uh, Roman numeral 3, if we don't really know what the eluting strength means, we are probably less certain of that. So I would put Roman numeral 1 after Roman numeral 3. I mean, sorry, after Roman numeral 2. And then I would put the least certain one, Roman numeral 3, at the end. So, because you're completely sure of Roman numeral 2, you're 67% sure, let's say, of Roman numeral 1, and 3, let's say, like 0% sure. And then let's go from there. So we want to start with what we're completely sure of, which is Roman numeral 2. So we're going to go through the choices and eliminate anything that doesn't have Roman numeral 2. So A is out, right? Now, everything else has Roman numeral 2, but now we want to place more of an emphasis on Roman numeral 1, right? So we want to see something that has 1 and 2 and not the 3 instead of something with 3, right? So 1 and 2, that's good because we're most certain of 2 followed by 1, so that's fine. 2 and 3 won't work because we are less certain of 3 being right than Roman numeral 1 being right. So that's out. And then D is the same thing as B, except it includes that Roman numeral 3 at the end. So at this point, we're 50-50. So always try to do that because, you know, there will be a lot of times where you're not going to be completely certain of the answer. So you just want to do the best that you can. Yeah. So, but this actually shows you that um, that Roman numeral 1 must be correct, right? So you could even use this to learn. Like now you know that temperature must play a role on that retention factor, right? Because we eliminated the choices that don't have Roman numeral 1 in it, right? So
Yeah.
Roman numeral 1 must be true, just as Roman numeral 2 must be true. And then I guess it just comes down to the Roman numeral 3 part. Um, and for that, you can see that we have a polar and a non-polar. And so there's something that's different. So a greater blank, like let's say this, we don't even know what that word means. It would make sense that since the methanol is polar and the pentane is nonpolar, that you're not going to have an equal amount of whatever. Something will be greater, something will be smaller, right? Um, so I think from there you can kind of see that perhaps Roman numeral 3 could be true as well. Even if we don't know that the word for know the meaning of the eluting strength. So I would go about it that way. So this way, like you can use your logic to maximize the points that you get without having to know everything. And what's better is that, you can then learn from like the question stem itself.
Yeah.
But yeah, I would say that the eluting strength, so like when we when I typically think of elution, I think of like some column chromatography, right? Where we throw something in and the stuff that binds to the stationary phase, sticks around, but the stuff that doesn't bind to the stationary phase, aka the thing that's soluble in the mobile phase, is what elutes first, right?
Mhm.
And so I think the eluting strength here would be uh, greater when using the methanol.
So you're saying eluting strength is
Oh yeah.
like,
Sorry. So yeah, the example that I gave is for a column type of chromatography, in which you separate them by having the something attached to the stationary phase, and the stuff that's soluble in the mobile phase elutes out. But in a thin layer chromatography, we don't really have that. We don't have we're not like letting the things that are bound to the plate, and we're not like separating it from the water, or the mobile phase like we are over here. So elution would mean something that would be similar, but it won't be exact. So we can say that if something has um a larger so okay, in this example, something that has a lot, like if I'm separating a molecule that has a really large affinity for the stationary phase compared to the mobile phase, that elution strength should be going up. And now if we apply it to this, right, elution strength should go up as the affinity for the stationary phase goes up. I would say to think of it that way. Eluting strength proportional to affinity.
it's the opposite of what I am thinking, or like think normally. Just because I think of evolution as leaving, right? Like
Yeah.
progress.
Yeah, me too. That's why I was thinking of this example, right? But it's just that for the TLC plate, there's no way to separate the mobile phase from the stationary phase, right? So what's in common with both of these, right? Well, what's in common is that the amount that elutes here and the amount that, I guess, travels up the plate here are dependent on the affinities for the stationary phase. That's what's in common.
Okay.
So just as this involves it leaving this thing here the things that travel up are going to have um a larger uh affinity for the mobile phase compared to the ones that would have a higher, if it had a higher affinity for the stationary phase, it would not travel as far up, right? But if we use
Yeah, I just want to make sure, what is the polarity of the stationary phase in the thin layer chromatography?
Oh, okay, yeah, I guess I should have mentioned that. So you're using silica, which is polar.
Okay, that's what I thought. And so if it's polar And when it says when used as solvents in the TLC procedure, you're using methanol and pentane as solvents. So this is like our solvent front traveling up. And okay, that makes sense, right? Because like methanol, because it's polar, it's going to be able to travel up farther in something polar.
Mhm.
Uh, which is the opposite of, I guess. Yeah, and I guess in TLC that's the case, and in the other example, it's not. Because in the other example, pentane would go faster because it has zero affinity for the polar,
Station
stationary.
phase. Mhm.
But in TLC, it's traveling through it, so it needs to have affinity to be able to like move on.
Yep.
Like I see. It's like the opposite. I see.
Yeah, yeah. So, but yeah, going about it, you want to process the Roman numerals, make some greater than hierarchy, go start with what you know for a fact, eliminate the choices that don't include that, and then think about what's left. So we answered our question that temperature must play a role without needing to know it, just from process of elimination. And then
Why does temperature play a role?
what's up?
Why does it play a role? Like, yeah.
So why does it what?
Yeah, why is it playing a role? I don't.
Oh, okay, okay. So we know that Roman numeral 2 is correct, right?
Oh, like I know why I just want to understand why temperature,
Uh-huh.
um, it,
Yeah.
like the tension factor depends on temperature.
Okay, okay. Yeah. So when it came to that, I was thinking like should I like explain it or should I like just so I'm gonna explain it, but prior to that, I just wanted to show that if you didn't know, now you know, and it must play a role now because you see it in those choices that are left. But yeah, the answer is that pretty much temperature is going to play a role in pretty much everything. And if you're, I guess like also think about when you do this TLC experiment, like you typically don't leave it open to the atmosphere, right? Like, do you remember like doing it in lab or whatever?
I had virtual lab, so I did this at home.
Okay.
So we got kids.
Did you have like the top of it open?
Yeah, it was all open.
Okay, okay.
It was COVID. Yeah.
So yeah, so usually when you do the experiment, like you're supposed to put something like over the top. Um, but let's think about that, right? So look, if the temperature was high and or as the temperature increases, you're going to have more evaporation. If you have more evaporation, you're not going to have as much of that as much of that mobile phase. If you don't have as much of that mobile phase, you're going to have a retention factor that would be lower than what it should be.
Okay, that makes sense. How like things are evaporating depending on like temperature.
Yeah,
Yeah.
yeah. And in general, temperature is going to affect almost everything in chemistry and stuff. Um, so always think of that as a thing.
Okay.
Mhm. Yep.
All right. Sounds good.
Yep. So
Yeah.
yeah, so you're doing really well, and um, I forgot what else I was gonna say, but I just want you, I guess, like the overall thing to see here is that you, well, I guess I don't really have anything to say, but yeah, you're doing well, um, and yeah, you can answer these types of questions. I guess what I was gonna say was like ideally, of course, you know, you want to be able to get the right answer and stuff like that. But a lot of times it's less finding what's the right answer and more um finding the ones that can't be the right answer, and going from there. So, and that plays a role in certainty as well. So that's why with these, like when we go over these questions, like I try to have like think out loud and show you like, okay, this is what, I'm thinking about based on the information that I'm having. And like instead of me just telling you temperature causes the evaporation, which will mess with the retention factor, I want you to see that it's okay if you don't know that, because on the test you can still figure stuff out. Because on the test you're not going to be able to look it up. So, you know, so all of this practice just means that you're getting to be a better test taker.
Yes. And
And yeah.
I think it is helping. Before I would be like,
Mhm.
um, not really following what I'm reading, but like reading it aloud has like allowed me to like follow the experiments more and like
Yeah,
understand passages.
yep. And then yeah, the stuff that we talked about with like the buzzwords and stuff um would be good to notice. But yeah, good job here.
And do you recommend or like what did you highlight them as you read, or just took a mental note of what they mentioned?
You can whatever helps you, because like sometimes people highlight too much and then it removes the point of highlighting. Sometimes people highlight things to refer back to. Sometimes people highlight things to help them stay active reading, like kind of like as they read something, like they highlight stuff just to keep their pace. So um yeah, I would say whatever works for you. Um but yeah, you have the right idea. Um you see figure one, you see a structure, identify functional groups. You see, you know, numbers, be aware of that. So like for example, the buzzwords here were like separatory funnel, extraction, um, yeah, stuff like that, I would say. So uh yeah.
All right, sounds good. I guess we'll meet tomorrow.
Yeah, yeah. Um yeah.
Yeah.
And then I guess yeah, and then I guess we'll see what to do for this weekend. But it seems like you're in a good place.
Okay.
Mhm.
Sounds good.
All right.
You world. Bye.
All right, take care. All right. See ya.